Well, hello. My name's Richard Campbell. I make a lot of podcasts, and I'm from British Columbia. And this probably doesn't impress Swedish people terribly much, but we do have bears in BC. This is a camera between my place and my neighbor's place. We call it the Animal Highway. There's just forest in behind us, and so it's fairly common. I only found out when I put the camera in for bears to take a good look. It's Wednesday morning, about 6 a.m. in the summertime, and that's garbage day in my neighborhood. So this guy's just dropping by to see if I put out my garbage early. He's pretty reliable, checks every week. You know, hope springs eternal. And that's kind of normal for us. And I mean, Norway and British Columbia, just not that different. We're big on the fjords, lots of rocks, trees, and ocean. But that freaks the Australians out. I mean, they got all the poisonous spiders in the world, but you show them a bear, oh my God. I've been doing this talk for a few years now, starting about 2019 with this, what are we looking at in the next decade or so of software development? And a lot of that knowledge for me comes from the podcast. Any .NET Rocks listeners? Oh, wow. Okay, great. I'm among my people. My friend Carl started .NET Rocks back in 2002, which is before the word podcast exists. I came on board as the co-host of show 100. Today we published episode, 1760-something. And that's really a talk show talking to smart people about what they're doing inside of the .NET ecosystem. Some stuff's more .NET than others. And it's a great way for me to learn, and I hope it's a great way for you to learn too. Free to download on your favorite podcast. Because I sort of live in both worlds of both development and IT, I also make a show called Run As Radio. We just passed our 800th episode every Wednesday since April of 2007, because starting out IT podcast as Microsoft shipping Vista seemed like a good idea. But that means I get to talk to security folks and sort of the IT world as well. And for a brief interval, just a few years, we made a show called The Tablet Show. We didn't really know where tablets fit in. And so we made it stand on its own. And after a couple of years of that, we realized it made sense to become just part of .NET. And so we rolled it back into .NET. But I'm trying to predict the future. I'm trying to look forward 10 years or so, and I'm reminded of Niels Bohr, who said that prediction is very difficult, especially about the future. Niels Bohr, famously, his PhD thesis is the atomic model. So this is, you learn this in school, right? The idea that we have an atom is a nucleus of protons and neutrons with orbiting shells of electrons, which is actually a lie, but it's a useful lie. And it helps us understand the beginning of quantum theory. So that's 100 years ago. 100 years ago, we were just coming up with this idea of what an atom looked like. And now look what we do with them, for better or worse. My favorite Niels Bohr story is on an exam question, when an exam question that said, there is a tower in front of you. You have a barometer. How would you measure the height of the tower? And Bohr said, well, there's a bunch of fun ways to do this. I mean, I could take the pressure at the bottom of the tower, get to the top of the tower, take the pressure difference, calculate it that way. I could get to the top of the tower, throw the barometer off, and time how long it takes to fall. But my preferred method would be to knock on the door and say to the man inside, hey, if you tell me how tall this tower is, I'll give you this nice barometer. There are many solutions to problems. We're in the 2020s. Welcome. I'm sorry it snuck up on you like that. We live in a cloud and a mobile world, for better or worse. This is the new environment we work in. We generate astronomical amounts of data these days. These electronic digital extensions of ourselves are perpetually gathering and spewing data about us into the cloud. Constantly. We are all cyborgs. That's what smartphones actually did. They became digital extensions of ourselves. We normally think of them as like the Terminator kind of thing, because you want to put the electronics in the inside, but I mean, ew. And also, don't slow down my upgrades. I need a new phone. People start using terms like big data for all the data I'm gathering, but there's not a lot of big difference between big data and a big pile of shit. So I think that's from Jurassic Park. And what's his name, the scientist guy who everybody thinks about, that life finds a way. It's like, no, when he walked up and said, that's a really big pile of shit, that's my favorite line from Jurassic Park. this is all stuff we know, right? These are trends that we've been on for a long time. More compute, more data, more clients, more points of interface. All those things have been going on for decades. If I look in the next 10 years, in these 2020s, what's actually going to change? What's going to affect what we do for a living? Well, the first and arguably the most important thing is that Moore's Law is going to end. It's somewhere in this next 10 years. Now, let's remind ourselves what Moore's Law actually is. Lots of people hear the term. They often equate it with marketing things because that's what marketing people want you to think. Gordon Moore was a scientist and technologist, one of the founders of Intel, and he observed in the 1960s, as they were starting to build the first microprocessors, that for roughly the same amount of money, they could double the number of transistors on a given integrated circuit every 18 months. Sometimes he said 2 years, sometimes he said 1 year. He never called it a law. It's not a law. Laws are things that happen anyway. Gravity's a law. Knock yourself trying to break it, right? Speed of light's a law. That's a tough one to break too. But Moore's Law is actually the effort of a tremendous number of people to continuously improve our ability to put electronic devices into very small bits of silicon. And we generally manifest this as an arc of CPUs, starting with the 4004 in 1970 up till current times. And this is a pretty good line. But it's only because we have a geometric progression on the left side here. We're going up orders of magnitude on the left side to create that nice line of increased performance. If I don't do geometric progress on that line, I actually go up. Normally, you get the hockey stick, irrelevant numbers, and then whoop, up the side, because we keep doubling that density over and over again. Now, this is all pretty good. If you like graphs, welcome to graphs. When I have to explain this to mortals, how do I do it? Well, we talk about computing. So, what's this? Warp drive from the Enterprise? No, that's this. This is a Cray XMP, circa 1985. This is the most powerful computer in the world in 1985. Cost several $1 million, typically owned by universities and governments. They only made a few hundred of them, consumed about 200 kilowatts of power. To keep the chips that were in it from melting, they were actually bathed in mineral oil that was constantly cooled. And it pulled out about 1.9 billion floating point operations per second. They used it for modeling nuclear explosions and calculating orbital trajectories. That's 1985. Fast forward to 2011, iPad 2, $800. Don't put it in liquid, that's bad, don't do that, right? About 25 watt hours of power in it, lasts about a day, if you're lucky, don't run flash. 1.9 gigaflops of processing power. So the same compute that was in the supercomputer is now in the iPad, and you play Candy Crush with it. We'll call that progress. But that's Moore's Law, that 26 years on, what was once an expensive computer surrounded by people in lab coats is now a device you hand to children, and they make the pictures bigger and smaller. And we know it's not that fast, right? That's 2011, it's 2021. When I talk about fast computing resources available to consumers, you think the 3090 video card, if you could find one. How much horsepower are we talking here for $1,500? Again, if you could find one. It's $3,000 on eBay. With 11,000 cores in it, it pulls down 36 teraflops. So it's about 18,000 times faster than the iPad 2. And it's about 350 watts. So hope you got a good power supply. And that's not the fastest computer in the world. That's a fast compute device that I can put in a regular PC. The top tier supercomputer today, the great-great-great-great-grandchild of that Cray, is currently in Japan. There's been a battle for supercomputers for a few years now between the Americans, the Japanese, and the Chinese. So every couple of years, somebody builds the next biggest one. Fugaku is the current leader at 7.3 million cores. 415 petaflops. That's a lot of flops. The estimate of the human brain runs at about 25 petaflops. That's the estimate. It doesn't map particularly well. And a couple of years ago, we built the first supercomputer that pinked that number. And then a couple of years later, because Moore's law, here we are at 415 petaflops. So that's 12,000 times faster than that 3090 video card, 220 million times faster than the iPad 2. Now, admittedly, this thing consumes 30 megawatts of power, so bring your own nuclear reactor. And they're about $1 billion, and there's exactly one. What do they do with this thing? Aerodynamic modeling, atmospheric models, the modern high-efficiency wing, things like the 787 wing and so forth, that's what these kinds of computers are for. And they're worth that money, right? You spend $1 billion on this thing because its ability to squeeze efficiency out of flight models is incredibly important and valuable. So we're far from done, right? I showed you a Cray XMP with 1.9 gigaflops, and then I showed you a consumer device 26 years later that has comparable computing power. I don't know if we're going to see this in the iPad 47, but it's reasonable to think in those terms, that we're going to continue to create compute. Now notice that this is massively multi-core. There's 7 million cores in the flipping thing, right? We have not been making individual processors faster since about 2000. We kind of hit the limit on that and just went more and more cores. And our software lags our hardware always. And you realize that Intel stopped increasing the speed of the processor in around 2000. That's when you started seeing Core Duo and the like. How long did it take for our tools to get any good at using multiple cores, right? We wouldn't see the parallel task library till the middle aughts. We wouldn't get async and await until 2010. So reasonable lag from software to hardware. But we were talking about Moore's law ending. So what does that actually mean? Well, this whole time, the way that this has actually happened is a lot of people have worked very hard, right? It's not a law. It's an effort. It's a goal that they're currently struggling with. The Intel approach was what they call the tick-tock approach. So for a year or so, they would work on a new process to densify transistors further. That's the tick. And then the following cycle, a year to 18 months, they would talk. They would take advantage of that increased density to build a more sophisticated architectured processor. Tick, tock, tick, tock. So roughly every 2 to 3 years, we would get denser chips over and over again. So in 1970, the 4004 had a 10 micrometer process. So, and now in the 2020s, we're talking about 5 nanometers. Now, since 2018, Intel has struggled with trying to get down to that 5 nanometer. They struggled with their 10 nanometer process, struggled with their 7 nanometer process, and then struggling with their 5. There are other vendors that have had more success, mostly because they've actually developed the chips differently, but we're kind of banging in the wall here. Why? What's special about these 5 nanometers especially? Well, you got to get your head around how small a nanometer is. A nanometer is a billionth of a meter. Easy to say. Hey, we're software people. We know what kilobytes and megabytes and gigabytes are. The thing is, they're 3 orders of magnitude. It's easy to say them without actually understanding them. So I try and set in the context for folks. I say, hey, if I asked you to wait for 1 million seconds, I mean, we can all kind of relate to what a second is, but 1 million seconds is a lot of seconds. How long would you be waiting if I asked you to wait for 1 million seconds? It's like 11 days. That's a while. If I asked you to wait for 1 billion seconds, I'm asking you to wait for 31 years. So a nanometer is to a meter as a second is to 31 years. Nanometers are really small. They're inconceivably small. And we're busy making chips in this realm. So this is a pretty cool micrograph of the IBM process for making 5 nanometer. It's not actually functional. It's a technique that they're demonstrating, which is pretty common for IBM. But this particular picture is a scanning, tunneling microscopy picture of a silicon substrate. The bumps you're seeing are atoms. The tall yellow bumps are silicon. The dark blue bits are boron holes because we make doped silicon when we make substrates for integrated circuits. Here's the problem. A silicon atom is 111 picometers wide. When you're making a 5 nanometer process, you're talking about 45 atoms. Hope they're good ones. Right? You don't have a lot of room for error. Notice this pattern that you see 3 or 4 or 5 silicon atoms and then a boron hole. Now, think in 45 atoms wide. There's 3 or 4 boron holes in a given transistor at that point, at least on one axis. These are actually three-dimensional structures. Like everything I'm describing to you is harder than I'm actually describing it as. But you wonder why we're running into the wall? This is why. We're running out of atoms. There are things we can beat, and there are things we cannot. And the size of an atom is one of those things you don't get to tweak. It doesn't matter what they do in the MCU and Ant-Man. You're not doing that here. So, and again, remember what Moore was actually talking about was not what was possible, but what was cost efficient at the time with the process. That's why there was a tick-tock, that they gradually increased density. They would modify the process to make it a little bit smaller without disturbing too many things so that they could get it done in a year or so and still be valid, be able to produce it at scale. That they're going to make billions of these per chip, billions of chip, for roughly the same price. The price of a commercial CPU largely hasn't changed in decades. The top of the line will be around $1,000 US. The cheap ones will be down to around 100. And they go down over time. And they've maintained that practice. So, we get to live on top of this remarkable substrate, and it's hitting its limit, right? That's the concern. So what's going to happen? Well, one of the downsides to us constantly improving, having this constant improvement in the existing CPU architecture is we have not changed the architecture. Every time Intel attempted to make a different kind of processor, they failed. The x86 architecture was largely defined in the middle 1980s, and every single one of the original 68 instructions of the x86 instruction set is in your processor today. By the way, even if you're running Apple, because they emulate the x86 instruction set, because it's that pervasive, right? We are carrying 40 plus years of architectural baggage with us. We keep patching it and modifying it to keep it going, but it's bloody complicated. It carries a lot of history with it to keep old code running. But it's not the only architecture. The ARM architecture, which, by the way, originally an Intel product, they decided they couldn't make a business of and sold to TI, who then sold it off to TSMC and a bunch of others and became ARM, is a much simpler way to architect chips. And so it's why it was initially built for phones, and it's now scaled up into larger devices. The ultimate manifestation of this now is Apple's M1. And if you've played with an M1 machine, you know what I'm talking about. Now, the important thing to understand about M1 is it's not incredibly dense. These are not 5 nanometer circuits. They're not even trying for that. What this is the ultimate manifestation of system on a chip. Rather than having discrete components for your CPU, for your GPU, for your memory, it's all in there. 8 cores of processor, 8 cores of GPU, a 16-core neural processor for doing neural processing, and 8 or 16 gigs of RAM. No upgrades, please. But because they're all on one common die, their communication speeds are impeccable, they're perfectly matched, minimum error problems, and the consequences is easily the nicest compute device we have at the moment. For better or worse, right? That's where we are. We're seeing, and this is one of the aspects of this talk I've had to change, because of the past couple of years, I predicted, hey, we're going to have this competition architecture, and it's mostly going to be ARM becoming bigger. Here it is. The first real shot at this emulates x86 instructions faster than the best Intel chips. Now what are you going to do, with your legacy baggage? This has a huge impact on how we build software. Lagging, of course. Right? We're going to be a few years behind this, but when you want to predict the future, you look at the road that we're already on. So I look at these architectures and say, how is this going to be manifest in the way we write code 5 to 10 years from now? I'm going to change gears. We've talked about our base hardware, the thing that's in every one of our machines. Let's talk about the actual largest problem in compute today, which is connectivity. Right? The one really constrained resource is still the wire. We've done everything we can to make the compute faster and better, but how do I talk to other compute units? So you may have heard this thing about 5G. 2 or 3 years ago when I would talk about 5G, everybody's like, that's the future, right? It's like, that's what the cell companies would want you to believe. And they tried really hard. It's nice that it's shipped now, and we're all terribly impressed, right? The idea of 5G is important. The main thing that they've done is they've expanded the available bandwidth for wireless communications. That's the fundamental limitation. You can't beat the speed of light. The higher frequency you go, the more data you can pass per cycle, the less effective it is at transmitting at range. Lower frequency radiation transmits greater distances, moves less data. So we've been using 2.4 megahertz for Wi-Fi and other common data communication, cell included, for a long time, and it's pretty good at data, but we've created a lot of devices now. The popularity is so huge that bandwidth's pretty much saturated. And so 5G adds up to 20 gigahertz, not just 2. And that moves a lot more data, except that it can't go through some things like windows or trees, which we both have a fair number of. And so as the telcos pushed the idea of this high speed for 5G, they put it in a lot of paces, but you'll find if you have a 5G phone that you're spending most of your time on 4G anyway. It's only when you happen to get the exactly right angle on a 5G node that you're going to get those higher speeds. That's sort of reality. It makes the question, like, why did they push so hard to put out 5G? And one of the reasons is the satellite networks, is Starlink. Anybody got Starlink? You guys are far enough north, like you run these things. I've got one in my cabin. It works. It's impressive. So Elon's managed with his cheap rockets to fly about 2,000 satellites into low Earth orbit and put them together in a mesh network that can provide you with reasonable internet. I think it's more popular with folks in North America because they hate their ISPs. Now, I'm not thinking anybody loves a cell company. They're not very lovable. But because you're angry with them, you decide you like Starlink better. What you'll get realistically from them is about 15 megabits up and 150 down. And that speed will continue to improve. And this is not something you're going to get out of a phone. The receiving antenna is the size of a pizza box. And it needs to be mounted, and it needs a completely clear view of the sky. No trees, which is not easy to do for a lot of places. But it is an alternative for worldwide connectivity. And certainly in crisis areas, in areas with limited infrastructure, in emergency zones and so forth, the ability to have data on demand, basically by snapping a dish down, snapping one of these planar dishes down and having it find the satellite and go to work, it's pretty compelling. If you're living in a part of the world where you have symmetrical gigabit fiber, this thing will not impress you, right? And lots of, we're very much living in the Western world here, in this room at least, and we know we got a lot of bandwidth. It's not that big of an argument. 5G, cell, and satellite are not going to impact fiber. There's an advantage to wires. They carry a lot more data in a lot less space. It's why we generally don't use satellite relays for internet at all. We've laid undersea cable. It's shorter. Geostationary satellite orbit is 36,500 kilometers up. That's 300 milliseconds each way. You're not going to enjoy Call of Duty that way, right? That's why we lay the fiber on the ground and through the oceans, so that from here to New York is less than 100 milliseconds, right? It's 50. Increased communication skills, increased and smaller chips and less expensive chips mean the proliferation of devices, huge proliferation of devices. I don't think the Internet of Things is a good term. I have a hard time arguing with the Twitter account, the Internet of Shit. I do not need an IP address in my fork or my toaster. But we're doing it, for better or worse. We're creating compute devices everywhere. And that's useful in a lot of ways, as long as it's reasonably well controlled. We have the resources for it. We just have to be responsible with it. And so far, we're not being. Let's be clear. There's a reason why Troy Hunt is as busy as he is. Every time you make another device, you create a new exploit. One more force acting on us, and that's the pandemic. We're in the latter stages. New variants excused. Back in the spring of 2020, Mr. Nadella made that point that we did about 2 years of cloud migration in about 2 months. When we send everybody home, suddenly people have learned how to scale VPNs in a hurry. and shipped a lot of product, a lot of resources off, and sent a lot of computer home. We'll be studying the effects of the pandemic on society for decades. We're still in it. We don't even realize really it's a historical event. Mostly it's still a nuisance. For some of us, work just didn't change all that much. We didn't like people before this thing. We don't like them after. We've all gotten better at Zoom. Okay. We all have better camera rigs. A lot more of us know something about OBS. We don't think green screens are that weird anymore. We just don't like them. But that's not the real impacts of the pandemic. I mean, the real impacts of the pandemic are the impacts on the economy. We have revealed the instabilities in the global supply system that have always been there and have been warned about for some time. But now that we've actually put stress on it, we can see the fractures, right? The mess that is North American container shipping. It's literally like a traffic jam. It's just going to take time to unwind. There's no way around that. And the various bits and pieces of interruption and just-in-time production have meant that a lot of things got 3/4 finished and never completely finished because they're missing a component, right? The number of cars that are sitting in yards because they don't have their ECUs, their controllers. So you've tied up all that money and all those resources for almost finished product. Like, that's a long time to resolve. And the longer those products sit unfinished, the less valuable they become. It's part of shaking that out. What does that mean for us as software developers? Oddly enough, we're remarkably resistant to most of this. We're abstracted from a lot of it, but not everything. We've had an unprecedented run this past 20 years or so, the Great Recession notwithstanding. Coming out of the dot-com bust in 2000, 2001, the demand for compute has only grown. The demand for programmers has only grown. It's normal for us to have the majority of folks working with us have less than 5 years experience because the growth rate's been so stunningly high. Anybody who could write some code is pretty much as busy as they want to be. The difference now is that companies are cautious, more cautious than they have been. They're more concerned about return on investment for software. Now, I've been writing code for 40 years. I came into this in the 80s. Where we were in a pretty nasty economic downturn. You had to be pretty sure that the software you built was going to be, the cost of that was going to be less than the productivity that provided. We haven't had to think about ROI for a while. But the question I ask developers when they're saying, like, what's going to happen? Is like, do you know how your company makes money? Because it's not with you, right? At best, as software developers, we build tools for the folks that make money to be better at making money. That's at best. Sometimes we're several more orders extracted than that. We make the tools for the guy who uses the tools. He works with the guy who talks to the guy who actually makes the money. Right? We can be a long way removed from how this company makes money. And if you cannot map the code you're writing to the way the company makes money, your project's in danger, right? Your leadership is concerned. This has been a pretty hard shakeup, and it's not over yet. You may have already felt this, or it may still be coming for you, but being savvy to the profitability of the company and how that works and how you and your team work into that and shaping your behavior, how you talk about your work and the things you're working on to those things, you will help your company and you will ultimately help yourself, right? These are good skills to have. They have not been important for many years. We've been able to ignore them. It is hard to ignore them right now. Let's talk about fun in the webland. The jury's basically come back, and the browser is the smart client, right? For the most part, it's one. It's, for me, as a guy who makes a lot of podcasts and talks to folk, my questions all the time these days is like, are we going to care about client development again, or is it just going to be the browser all the time? Now, the IT guy in me, which lives in, because I live in both camps, says, oh, it's the browser all the time. Thanks very much. I don't want you installing software on computers. That's how bad things happen, right? The browser is the security context for executing most tasks. And the increasing sophistication of the browser and the general cooperation between the browser entities. I mean, essentially, Edge and Chrome are the same thing engine-wise. It's all Chromium all the way down. You can talk about the variations, but it doesn't mean all that much. The only real problem child is Safari. Safari is the new IE6, right? And I don't just say that as a joke, right? Like, why did IE6 become IE6? Because it was the default browser in XP, which is the operating system that would not die. And it was shipped before CSS1 was ratified. So it had its own freak show version of CSS that didn't match anything else. But it wouldn't go away because of XP. That's what made IE6 IE6. Well, let's look at Safari today. It's the default browser on Mac OS and iPad devices. It isn't compliant with standards. You can't get them to upgrade, and they won't use a different browser. It's the same flipping problem. And so you end up writing if Safari code. Welcome to IE6 land. Where's DHH when you need him? But they have all finally gotten the PWA board, right? This idea that we can build manifests for browser behavior. We can spit an icon out. We can call to services inside the device. Like, you can pick a pretty robust app these days. You can also make really bad ones, but that was always true, right? You can make really bad client apps too. But if you work hard in this space, you can do good things. And we're at NDC, where our friend Steve Sanderson first showed off, hey, there's WebAssembly. Can we stuff .NET in there? And made poor David Fowler's head explode, right? I almost thought it was a prank by Sanderson. Like, he's like, look at this. This isn't for real, but you can do this. And now it's a product I think a lot of people like. That we're continuing to extend the ability of the browser to be a comfortable programming environment in different languages now. Maybe that's the client. I don't want that to be true, personally. And I'll talk as we get further into this about why, because there's some good reasons why the browser shouldn't be the default for everything. But the enterprise architect in me also says there's a good reason for the browser to be, for a lot of things, the platform. Most of the software we need to build is pretty straightforward, forms over data kind of problems. This is not an area for innovation. This is an area for reliability, consistency, and maintainability. And so these tools seem to serve that pretty well. That being said, any predictions of the death of JavaScript are grossly exaggerated. It's a very popular language. It's not getting any less popular. Hey, golly, people are still programming COBOL. I do make a show about .NET, so I shouldn't be rude about .NET. I have nothing bad to say about .NET. .NET probably bought me a house, I'm pretty sure. .NET turns 20 in February. 20. That's interesting. Now, and some of you may know, I've been working on a book on the history of .NET for most of the history of frickin' .NET, it seems now, but it's not a lot of languages and platforms that continue to be relevant that long. And the predictions of the death of .NET have happened a number of times, but they've reinvented themselves a couple of times. And what's interesting for me is that we have lived for the past 20 years or so in a layer of sufficient abstraction from hardware that we're immune to it. We've been able to program in .NET on x86, on x64, on Itanium, for the 5 guys who did that, and on ARM, and every other processor that comes along. That's Microsoft's problem to make sure that our code compiles on those platforms. So we don't care about the underlying hardware anymore. It's one of the reasons that things persisted so well. And now they've shaken off their bindery to Windows, sorta. Right? I mean, .NET came into this world as an alternative to Java. Don't believe the old hype. That was the truth. They weren't allowed to do Java anymore. Microsoft made a very good version of Java, arguably too good. It upset the Java people. And now so they made their own thing, designed to be an enterprise architecture development environment against Windows. And then operating systems just became less important. And remarkably, they were able to untangle it and do it and make it live without it. That's surprising and is ultimately the interesting part of the book, is how does something built to run on one platform walk away from the platform? And it's thriving accordingly. I think another aspect that's important for all of us is containers. And that's because they're a new kind of virtualization that's become important. More and more, we're not trying to press against the edges of what software can do. We're trying to make software that's more sustainable, lasts longer, easier to maintain, causes fewer interaction problems, causes fewer security risks. This layer of abstraction against the operating system is an approach to that. That's pretty universal. The real thing that happens if you spent time trying to put any of your software into containers is you have to build a manifest. You have to tell the container what resources you need and how you're going to communicate and where things are going to go. It's good if you know those things. Otherwise, it's really hard to put stuff in containers. But it's also the question that every InfoSec guy's been asking you for the past 50 years. And now you're answering it in code, so it might actually be right. And if it isn't right, it doesn't work. I mean, that's another good solution. So we're seeing virtualization penetrate much more deeply. You're starting to see the client side start thinking serious about virtualization as well. It's reasonable to predict in the next few years that the norm will be that every application runs in a kind of container where you tell your operating environment, this is my manifest, this is what resources I need, and they can decide whether it can allow it or not, and you're basically not visible to any other piece of software. Cross-software implications just aren't going to exist anymore. What does this mean for us today? You don't have to do this right now. You don't have to be at the forefront of this, but it is in your best interests to be aware of the effects of your software. What resources does your software demand? When you write code, be very explicit about when you're going to call out to a service, when you're going to expect access to a resource, like having those things in place. And containers will help lead you down that path, and other tools as well. But that behavior is only becoming more and more important. Now, if this is blowing your mind, you're like, I don't know how I stay in this industry anymore, that's okay. Change is frightening. And there's not one way to do a career. I'm not here to tell you what you need to do next. I'm only telling you a range of possibilities and things that are going to be affected and how you could respond to them. But there's a bunch of ways to lead a successful career. You don't have to do it one way. You don't always have to be the person in the new bits. I've seen plenty of folks with very successful careers that have gotten good at a tool set that they're happy with and have stayed with organizations that want that tool set and been the maintainer. Now, the transformation of this is often we get into a tool set when it's new and it's fresh and exciting because we are new and fresh and exciting. And so we play that game for a while and ride up with it as it grows and matures and becomes things and gets bigger and bigger, and then it starts to peak. And some folks that like the new and cool thing are going to spin off and do the next new and cool thing. Some folks are not. They're going to stick around. And so your markets may actually shrink, but your value in that market doesn't because there's still demand for what you're doing. The actual death of a technology is a pretty rare thing. It takes a long time. I've met folks that are still happily maintaining Silverlight apps, right? Because just because Microsoft suddenly didn't work on the technology anymore didn't mean it burst into flames and evaporated. It still works, right? And now there's Open Silver, where now they've built an open source implementation that's very Silverlight-like. It literally will convert Silverlight apps into WebAssembly applications. Interesting. So you can step off the new tech stack and pick a stack you want to work in and have a successful career, do good things. So you find out what makes you comfortable. Are you going to keep running with the latest and greatest and be part of a growing market piece, or are you going to focus your expertise more and more on a smaller market piece? There's not a right way to have a career. You know, the only thing I would hope is that you're intentional about it. That I know where I am and why I'm here because I want to do this and I want to work this way. That's good enough. You'll be fine. There's lots of opportunity. So now they've said that, let's talk about other opportunities. This is a little perilous for me, considering the room I'm in, but I would argue ignore the Power Platform at your peril. There is a non-trivial chunk of business problems that can be solved with these tools. This is the 21st century version of Microsoft Access, right? It only sounds funny. But what did those tools do then that these tools are doing now? They took non-professional developers, domain experts, and gave them sufficient tools to solve problems for the domain. Domain expertise turned out to be the more valuable resource than programming ability. Not saying they didn't make ugly things, because they did, right? But this is a modern, low-code tool set based on mobile and cloud that can solve a non-trivial chunk of problems. And where you hit the limits of these tools, there's extensibility capabilities that professional developers can take advantage of. I'm not saying you should start working on Power Platform. I'm saying ignore it at your peril. None of us are getting to the bottom of our to-do list, right? No, right? Even through the pandemic, the to-do list didn't go away. It just got shuffled. A lot of stuff that was important became less important. Things that weren't as important became more important. That's the only thing that happened. Bottom of the to-do list, never seen it. It's on the next page. I don't make it past the fold. So if a group of folks who have areas of expertise that they can solve certain classes of problems that are down on your to-do list and make them go away, those people are your friends. Help them. And when they hit the limit, or they run into the walls, you can get them over them by building extensions and by building services that they can call into. The other reason I know this is important is there's like 15 different variants of this, not just inside of Microsoft. Salesforce has one, Oracle has one, like all of the big cloud players are making variations on this theme. That's a sign that they're feeling around for the best way to solve this problem. It isn't going away, it's only getting larger. And it's going to create a new generation of developers. The same way that the Accesses and VBs of the era did. It's a good new wave, and it's a good new wave. It's going to be an interesting few years as these things grow in. If you want to be more leading edge, let's talk about what replaces the smartphone, because the smartphone is ripe for replacement. This slab of black glass has been a slab of black glass since about 2007. You know, before 2007, phones were cool. They had slide-out keyboards and pop-up antennas, and like they were different. Now they're all slabs of black glass. We're basically been done for 15 years, right? I mean, they're bigger or they're smaller. They have one camera or two cameras or three cameras or LiDARs or like how many cameras do you need? But they're basically the same. The interface has matured. It's kind of done. What they have done is penetrated humanity. There are 4 billion smartphones, smart devices operating on this planet. That's one for every adult. We are all cyborgs. We all have access to more information. Quality of information is questionable, and more ability to communicate than at any other time in humanity, by a long way. You know, the US president in the 1970s didn't have as much communication opportunities as anybody with a smartphone has today. It's profound what's happened. The question is, where does this hit its limits? What can't it do? What can we go further with? And that's where the augmented reality devices come in, the visors. Now, history has taught us that the incumbents will not disrupt their own markets. So don't expect AR from Apple, right? That seems unlikely. Maybe Microsoft, the HoloLens is pretty interesting. More likely a third party. Now, what's the problem? Well, first off, what can this do that a smartphone can't do? Well, the main advantage that it has is its position being on your head. So its ability to see what you can see and to add information to it to augment your reality. We're already seeing applied versions for certain vertical markets. This is a mock-up example of someone doing maintenance on a piece of factory equipment where the augmented reality is walking them through the checklist. Not just that it has the checklist in view, but it can actually highlight the component they're supposed to be working on and won't provide the next step until it can see they've completed the previous one. So I've seen this done for airliner turbines, for jet engines, where what Pratt & Whitney was excited about with this, right, sort of the hard hat integrated version of it, was that not only was the guy walking through the checklist precisely for how to service this engine, he was creating a detailed video record of it while he was doing it. Right up to the point where when he went to replace a part, he would hold the part up to the headset so that it could read the QR code and identify this is a real part. This is the exact piece that we ordered that's going into this engine. And at one point, when he's looking at a blisk at one of the components on the turbine and he's concerned about cracking on it, he requests an expert who puts their own headset on in a different city and now looks through that person's eyes at what they're looking at, and they decide on the change. And that's included in the record as well. And that device, and we're talking about the HoloLens 2, is a $4,000 device. It's not a consumer product, but when you have a group of experts working on a $50 million engine, running the infrastructure for a bunch of $4,000 devices makes a lot of sense. What the HoloLens 2 reminds me of right at this particular time is the BlackBerry phone circa 1997. The old Crackberry from West Wing, right? Because the internet was not big enough to support this. So the way that they actually made it work is you ran a lot of infrastructure inside of your enterprises. The devices were $1,000+, and they only worked with a big organization that ran a bunch of infrastructure. Sound familiar? That's exactly how they're operating HoloLens right now. So we're kind of at the BlackBerry phase with some of these augmented reality devices. Certain verticals that are sufficiently high priced and are willing to operate the infrastructure can be successful with them. Now, from a hardware perspective, This is a complete computer integrated on someone's head. That's a hard problem. But we've already talked a lot where Moore's law is at and how much more compute we have in headroom for us. No pun intended. This can only get better. The next couple of generations, the next tick-tocks of hardware going into augmented reality will shrink the device down. Not that I'm concerned about how dorky the device looks. That doesn't matter when the experience is compelling enough. Once upon a time, walking around like this was dorky. Turns out dorky goes away when everybody does it, right? So you fell in love with a smartphone when somebody else had one and you said, hey, can I try it? And then you wouldn't give it back. That's the same thing that's going to happen with the headsets. So I own a Google Glass. I have been a glass hole. But let me tell you the actual experience of wearing a Google Glass in public. People's initial reaction is, can I try it? After they try it, and it's not compelling enough, now you're a glass hole, right? Once the device is good enough, the social constructs change. If I had a pair of goggles on and I was having a good time, and you said, can I try it? And I put them on you, and they were that good, you wouldn't care you were wearing them. They're just not that good yet. HoloLens is pretty good. First time I actually was able to spend time with HoloLens, I wore it until the battery ran out. I was surprised. I didn't expect it to be as good as it was. It was also too expensive and too fragile, and the software development process was too difficult. So we're not there yet. However, we're getting there. We're close. What does this mean for you? Well, for some folks who want to jump into the leading edge, and there's people already doing this, there's HoloLens development going on. It's largely done in Unity, which is C#. You got to live in 3D land, which is hard, but it's learnable. For better or worse, when new platforms like this come along, and you think about how disruptive this platform is. You know, phone was disruptive enough, but we did MDOT for a long time. The tablet's what really made a mess of things. Okay, we have to take touch seriously. Touch is just a more sophisticated version of mouse. And we unified pointer behavior between mouse and touch, but we were still screen, keyboard, touch, mouse, or pointer, right? That's our current set of UX interfaces. And those just don't apply here, right? Suddenly, touch is gorilla arm problem, right? It's hard to do touch and gestures, and I'm doing HoloLens gestures. They're already embedded in me. But the HoloLens 2 has an eye tracker in it. So we can look at where you're looking. And that's enough of a hint to pull up more details. Right? So it's just the fact that you're looking at something long enough means you should pull additional data on that. It's interesting to think about two people meeting with HoloLenses on and having like a business conversation. And now you have this digital agent that's heard the whole conversation. It's like, okay, well, let me make that lunch appointment you talked about and draft up the minutes of that conversation so that you can agree to it. Heck, we could do a contract face-to-face with a pair of HoloLenses and have the handshake as part of the video that's the contract. But there's an interesting bunch of workflows that come from this ultimately. The programming model is going to be a struggle. The hardware is not quite there yet, but it's close. And it will have an impact on what we do. It's the only thing I can see that will significantly disrupt the phone. But this is the phone's replacement. All right, last couple of things. Artificial intelligence. I did my AI talk yesterday. Anybody catch it? So, you know, I make Fallon Hal for a reason. Hal's the first time most people ever heard the word artificial intelligence. He was in a movie, and he tried to kill everybody. That's our relationship with artificial intelligence. The reality, of course, is artificial intelligence is a term you use for a technology that does not work. As soon as it does work, you give it a new name. Right? And that's why we have vision systems and machine learning and deep learning and predictive analytics. Those are all former AI technologies that made the mistake of working. Now they're a product. Well, it's not, when someone tells you, I have a new AI technology, so they're great, tell me what you've got that doesn't work. Because you'll have a better name than that. It's like, and if you want to sell a technology based on neural understanding, don't call it AI. Give it a different name. Is it impacting development? Anybody hung out with Copilot? Or played with this thing, with the gaming tool? This is the codex, right? This is using GPT-3, which is the best language interface we've developed so far, to help you write a game, where you literally just express what you want in the game as words, and it writes the code for you alongside. In the end, AI is not actually intelligence, a terrible name. These are clever tools. This is IntelliSense going ++. The developer's still needed. That's not going away. It's just that we have better and better tools doing it. These aren't a threat to you. These just can help you work faster. It's the same reason you played with Code Rush or ReSharper or any of those other devices, those tools that make your Visual Studio experience better or whatever dev stack you like. You use tools to go better. This is more of that. Just remember, science fiction, HAL, is messing with your brain and making you think about it wrong because they gave it a dumb name. Right? These are just tools. One last thing in the last minutes, we'll have a little fun. Let's talk a little bit about quantum computing. Quantum computing is not going to change everything. It is not going to replace Moore's law. Quantum computing works on particular sets of interesting problems that are incredibly important to our civilization. Whether they're important to us is yet to be seen. And I might be wrong about this, but probably not. The first set of problems, first off, the encryption problem is a red herring. Forget it. It is not relevant. By the time we can actually smash modern encryption with quantum computers, we will need quantum computers with an excess of 4,000 qubits. Right now we're at 50, and we're struggling to get higher than that. And the only reason that quantum computers can smash through encryption is that we're using prime-based encryption. We don't have to use prime-based encryption. There's plenty of other encryption techniques that do not use primes. We used primes because back when computing resources were rare, these were efficient. These days, this is not that big of a deal. We can change encryption strategies. But long before we could build a quantum computer that would do a thing on encryption, we could change the world in very important ways. In agriculture, there's a process called crop rotation. If you keep growing wheat in the same piece of land year over year, season over season, the wheat gets sicker and smaller until it won't grow at all. And so millennia ago, our early agricultural cousins learned that you rotate crops, that after you grow wheat, you grow beans. And then you might grow another animal crop like goat grass. And then you leave fallow for a year, and then you can grow wheat again, sustainable. We beat that with fertilizers, right? Our ability to use the Haber-Bosch process, which came out of World War I, because it turns out fertilizers and explosives, kind of the same thing, nothing like war for advancing technology, allowed us to put nitrogen back into the soils, which is what crop rotation was doing for us. That you would plant different kinds of crops that would replenish the soil, and then you could grow your regular cereal crop again. But we've also studied that process. So there's a rhizome that grows on the bean plant. And that is a parasitic growth on their root system that captures nitrogen from the air and combines it with the hydrogen to make essentially fertilizer that is affixed into the soil. And after you harvest the beans, you plow the roots back in. That's what repopulates the soil. The actual enzyme that's involved in doing that is called nitrogenase. We've known about nitrogenase for 200 years. Nitrogenase somehow, chemically, takes nitrogen out of the atmosphere and hydrogen out of water and combines the two into ammonia to make fertilizer with no energy. The Haber-Bosch process, which is the industrial way that we do this today, is 1% of all power consumed on this planet. All right? That's what it takes to make that much fertilizer. And here's a plant that does it. All we got to do is figure out nitrogenase. Now, the nitrogenase interaction is actually a catalytic reaction between molybdenum and iron. And molybdenum and iron have a lot of electrons. And that electron interaction is so complex, it's 2 to the 170th possible combinations of electron interactions. You will never solve it with a classical computer. But a 200 qubit quantum computer should be able to knock it out in an hour. Now, that doesn't solve the problem. Once we know what the interaction model is, then we can start working on, can we recreate that interaction model chemically? Can we actually do the same kind of catalytic reaction? But if you think about what that would do to our ability to grow food, if you could make the kinds of fertilizers that a given plant needs in its location with a watch battery, not having to make it in an industrial plant, ship it in barrels, and spray it on soils. You could do it way more efficiently. That is one of about 300 important chemical interactions that quantum computing can deal with. We fake our way through how batteries work. It's literally alchemy. We put different combinations together and we test them to figure it out. Because the electron interactions are too complex. Quantum computers can tear this apart. We've learned enough about superconductors today to know that it's actually a state of matter based on different combinations, conditions of temperature and pressure. But we can't actually model it. Too many interactions. Quantum computers can knock this out. Every one of these kinds of solutions leads to new technologies that make a substantial difference for society. They're very cool computing problems. They're also deterministic computing problems. Once you solved them, you don't really need to solve them again. So what do we need lots of quantum computers for? Like now you get back to the old James Watson or Thomas Watson's statement. I think there's maybe a world for 5 computers. We're kind of right there at quantum computers right now, where it's like, I think we need a few dozen, and then we can work our way through all these problems, and then the question is, what are the non-deterministic problems that we need this kind of compute for? I'm not saying there aren't any, I'm saying it's not obvious. I don't know that there's a non-deterministic quantum computing version of Candy Crush that makes it worthwhile to get quantum computers down to the point where they fit inside of tablets. I got invited to speak on a quantum computing podcast, and I'm not an expert in anything. I'm a professional storyteller. But I did put together the narrative of how quantum computing is going to evolve by matching it to how the mainframe computer evolved, how traditional computers evolved. We didn't start out with transistors. We had transistors in the 1940s. We didn't put them into computers until almost the 1960s. Shockley, who was the guy who ultimately created the company that would lead to becoming Intel, was one of the people who was involved in the transistor. And when he was trying to figure out how to make it into the integrated circuit, he needed so much computing power that he couldn't do it in a traditional way. He actually had to use a mainframe computer on vacuum tubes to model how to build an integrated circuit. And I wonder if that's not what actually is going to happen with quantum computers. Right? Quantum computers right now are bespoke computers like the mainframes of the 1950s. Each one of them is unique. They get their own name. Right? Google calls theirs Sycamore. The same way that the early mainframes are called things like ENIAC, before we actually turn them into producible, reliable devices. So perhaps the early versions of quantum computers are going to be the devices we need to model architectures to build the reliable qubit that will make quantum computers more readily available. I don't know if it's true, but it makes a lot of sense, and it is going to happen in the next 10 years. Making them a routine device is interesting. We can't think of the problem space any more than Thomas Watson could think of the problem space when he was selling the mainframe. He could not conceive of an iPad from a mainframe, even if he had all of those pieces in place. We don't know. We're not sure what's next. But I do know this. I'm in the room with the people that will make that future. Whatever we're going to do, whatever is possible, this is where it happens. Maybe I've seeded you with some ideas. I can't wait to see what you do with them. Thank you. Lunchtime.